Okay, let's start. So last time we studied about the linear independence or dependence. Okay. So given maybe these three vectors, v1 and v2 and v3, and then if they are linearly independent, and then when forming them into a matrix, okay, so this one is v1, v2, and v3, and so this is our matrix, and then we just construct the linear system of x1, x2, x3, and here this is our vector x, and then of course vector x should have a 3 elements because we have a 3 column vectors, and then we know that this one is working as a linear combination coefficient for each of these columns, right? So that's why we need to have a 3 elements, but each of these v1, v2, v3 can have a more or less than 3 elements, for example. So like this case where v1, v2, v3 are 4-dimensional vectors, so it is of course possible. And then the right hand side constant vector should be 1, and then in this case a times x equals 0, right? And then in this case we call it as a homogeneous linear system, right? And then the definition of the linear dependence of these 3 vectors is that this homogeneous linear system should have a non-trivial solution, which means that at least one of these x1, x2, and x3 are non-zero, right? So if we can find at least one solution that contains non-zero in the vector x, and then that's when these v1, v2, v3 are linearly dependent, right? And then also because by default we will have the solution of this all zeros, which is called a trivial solution, right? And then by default we will always have a trivial solution, and then if we have a non-trivial solution which contains at least one non-zero, and in that case this one or this homogeneous linear system will have an infinite number of solutions, right? Okay, then and then this kind of definition of this linear dependence was the same as the situation where we add one vector at a time and then keep increasing our span, right? And then if one vector can be represented as a linear combination of the previous vectors, and then that is the same as the case where that added vector doesn't increase our span, right? And in that case, also it is exactly the same as this linear dependence, right? So that's actually another definition of this linear dependence. Okay, and then also there was a third perspective about this linear dependence. So simply, if we have a free variable, after we change this matrix into reduced echelon form or echelon form, right? And then if we find at least one free variable, and that's when these vectors are linearly dependent. Okay, so there are these 3 different perspectives of understanding linear dependence. Okay, so let me ask one one kind of question that you may be a little confused of. So, for example, suppose the columns of an A are linearly dependent, which means we at least have a one free variable, and in that case, in this linear system, is it always true that this linear system has infinitely many solutions? So again, the question is, in this linear system of an AX equals B, so note that B is non-zero vectors. I mean, it can be zero vectors, but yeah, we are considering a general situation where B is non-zero vector. In this case, I told you that the columns of an A are linearly dependent, which means we have a free variable. In this case, does it have an infinitely many solution all the time? So simply, if we have a free variable, and then do we always have an infinitely many solutions? 네, 뭐죠? 자, free variable이 있으면 무조건 이게 해를 무한계를 가질 거냐? 맞아요? 참? 혹은 거짓? 참. 거짓. 참. 다시. 거짓. 거짓? Okay, so yeah, I'm satisfied that at least some of the students raised the hand, whether it's a right or wrong. Yeah, so the answer is wrong, because yeah, we first need to check whether this vector B is inside of the span of this columns of an A. Okay, so if it is satisfied, and then if we have a free variable, and then we will have an infinitely many solutions. But at first, if this one is not true, then yeah, we will have no solution at all, right? This one actually can be your one of your exam questions. And also, yeah, I'm not sure if you already know, but in our midterm or final exams, I really like to give you a lot of true-false questions. And for the last few years, I kind of did a little strict grading strategy where if you give a wrong answer on this true or false question, you will not get just a zero score, but you will actually get a negative score. Okay, so if you suppose you have a two true-false questions, and the first one you gave a correct answer, and then the second one you gave a wrong answer, and then in total it's like plus 3 points and then negative 3 points. In total, you will get 0 points. And in the worst case, in this case, I mean, yeah, in this case, some of the students get really negative points in total. So suppose you have like 0 and negative 3, and then your point will be negative 3, and then suppose for the rest of the questions, some students got all 0, like 0 score, and then the total score would be negative 3. Okay. Okay, so yeah, but anyways, the point is that you should be really familiar with all the tricky situations, and then you should be really clear about these situations. In terms of the number of solutions and independence or dependence or things like that. Okay. Okay, so let me give a really simple example that this one doesn't hold true. So first column, suppose first column is a 1, 2, 3, and then we added the first vector, and then suppose the second column was 2, 4, 6. Okay, 2, 4, 6. So that is like the case where those two vectors are coinciding with each other in terms of their direction, right? And then I give you, okay, so let's think about the span of these two vectors. The span will be still just a single line, right? and then if the B vector is actually outside of this span of this single line, and that's when we have no solution at all, right? And then yeah, maybe 3, 6, and if it's 9, and then this one will be the case like this, right? But maybe if I give you 10, then this is actually outside of the span. So in this case, yeah, if you do the row reduction, and then the second variable is actually your free variable, right? And thus these two column vectors are linearly dependent, but this doesn't have any solution at all, right? But yeah, if this one is actually true, where B is inside of the span of columns of an A, and then if we have a free variable, it's always true that we will have infinitely many solutions. Okay, so once the B is actually falls inside of the span of the columns of an A, and then yeah, we can guarantee that we'll have an infinitely many solutions. Okay. Okay, let's just briefly consider this example. So this example is saying they gave a two vector already, 3, 1, 0 and 1, 6, 0, and then yeah, we consider the third vector W. So we have a U, V, and then we consider, yeah, we have a third vector W, and then suppose these three vectors U, V, and W's are linearly dependent. Okay, so that is the assumption, right? In that case, yeah, let's see. This W vector should be inside of the span of U and V. So again, if U, V, and W are linearly dependent, in that case, it is saying that this W, or the third vector, should be inside of the span of U and V. And yeah, let's understand why. So in this case, we are utilizing the strategy of adding one vector at a time. Okay, so the first one, 3, 1, 0, and then 1, 6, 0 is actually outside of the span of the first vector because it's not in the same direction, right? And so we have only one vector left, right? But altogether these three vectors should be linearly dependent, right? But so far, when adding these two, they are not, they are linearly independent, right? So the last vector, we have only one chance, right? Because we have only one vector, one remaining vector, and so this remaining vector W, or the third vector W, should be inside of the span of these previous two vectors, so that they can be linearly dependent. Okay, so it's quite simple. Okay, so quite simple. And then also this theorem 8 is saying that, yeah, so we already covered this in this example where we have 7 variables or 7 vectors. Okay, so we have 7 vectors in total, but these 7 vectors are living in this 3-dimensional space. Okay, so we understand that these 7 vectors cannot be linearly independent, right? Because the first vector and the second vector and maybe the third vector, and then once we have 3 linearly independent vectors in 3-dimensional space, again our total space is a 3-dimensional space, and then the maximum number of vectors that can be linearly independent with each other, okay, that maximum number will be 3. Okay, so in that case we have 7 vectors, right? So in that case they should be linearly dependent, because once we filled up these 3 linearly independent vectors, and then that will cover the entire universe of R3. So we will cover up the entire 3-dimensional space. And so whatever vector we add, that should be always inside of the span of the entire three-dimensional space, right? I mean, the span of the previous three vectors, because that will be the same as the entire space. So we have no way to escape from that space. Okay, and also we understood the situation in terms of a pivot, right? So in this case, let's imagine it's a row-reduced form, row-reduced matrix, and then we have 3 rows, right? So 3 rows, and the maximum number of pivots will be 3, because the pivot will be the leading entry or the leftmost non-zero entry for each each row when after making it as a echelon form or reduced echelon form, right? So we have a 3 row, and thus we have at most 3 pivots. Okay, and then we now consider where these pivots are located in terms of a column location. So those columns containing those pivots, and then these columns will be called a basic variable. But those columns that doesn't contain any pivots, and they will be called a free variable, right? So in this case, 3 pivots at most, but we have 7 columns, and thus we have at least 1 free variable. Actually, at least 4 free variables, right? At least 4 free variables. Okay, so in that case, even without seeing the actual vectors, I mean actual 7 vectors, we can just easily answer that these 7 vectors are linearly dependent. Okay, so that is this theorem. So they are living in like 3-dimensional space, but we are given like 7 vectors where the 7 is greater than 3. Okay, so in that case, they are always linearly dependent. Okay, and then let's look at the last column in this chapter. So this is one really special but quite simple case. So what if we have 0 vector as one of the vectors in our vector set? So suppose we have p number of vectors, but one of them was actually 0 vectors, all zeros. Okay, so in that case, they are automatically linearly dependent. So again, if you contain 0 vectors in your vector set, and then they will be always linearly dependent. And let's see why. Yeah, we can use the original definition of the linearly independent or dependent. So let's consider like the 3 vectors. Okay, so the 3 vectors, and let's consider their vector equation form, and then we have to create 0 vectors, which is our homogeneous linear system. Okay, and in this case, suppose the second vector was actually all 0, and then can we find any kind of non-zero, non-trivial solution? Yes, we can, because we just simply set other linear coefficient as 0, and then for this 0 vector, we can set the linear combination coefficient as 1. So in that case, it's just a one non-trivial solution, because we are able to set at least one entry in this linear combination coefficient as non-zero value, right? So it's a really trivial and simple one, right? And so because we can find at least one non-trivial solution which contains at least one non-zero element, so these vectors are linearly dependent, right? And then also, let's think about this another scenario, another strategy of determining whether they are linearly independent or dependent. So the first vector and the second vector, and then suppose the third vector is actually 0 vector. And the question here is, still the same. This 0 vector that we are currently adding, is that, can it be represented as a linear combination of the previous vectors? So again, is zero vector represented as a linear combination of the previous vector? Yes, of course, because we can just simply set the linear combination coefficient of the previous vector as 0, and then we can always represent not this finger, but this point, which is our origin, or zero vector, right? So this zero vector will always be inside of the span of any other vector, right? Because we can simply set the linear combination coefficient as 0, right, for the previous vector. So yeah, we can represent this zero vector as the linear combination of the previous vector all the time, and thus they are linearly dependent. And also, yeah, that can also be represented as this. So we have this vector, and then yeah, we move this one into the right hand side. Okay, in that case, we will have this vector as a linear combination of these two vectors, which has the linear combination coefficient as 0. I mean, that is actually the same scenario where the third added vector that we are currently adding is represented as a linear combination of the previous vector by just setting the coefficient as all 0. Okay, so in conclusion, in this theorem, if you contain the 0 vector in your vector set, and then they are, yeah, just always linearly dependent. Any questions? Okay, so let's move on to the next chapter. So in the next two, yeah, so we have two sub-chapters left in the chapter 1, in the big chapter 1. And those two chapters are about this linear transformation. So linear transformation. So this transformation is actually the same term as function or the mapping. Okay, so the function and the mapping. And so let's think about the quite simple form of a function. So suppose we have this kind of mapping described by our arrow. Okay, so let me ask the question, is this a function or not? Is this a function or not? It is a function, but let me give another example. Is this function or not? So again, in this case, the arrow, I mean, yeah, the arrow arrived, I mean, multiple arrows arrived in the same target. Is this function? Yes, it is. It is a function. Okay. But what about this case? Is this function or not? Let's see. So it is not, right? Because we have to satisfy the rule that for this input values, for each of our input value, we should shoot the only one arrow, right? Only one arrow. We cannot shoot like two arrows, right? So that is a kind of requirement of our function. And then in this case, let me also think about this case where we have, let's see, like this case. So this one is not a function either, and this is, yeah, in this case it is because this guy doesn't shoot the arrow, right? So again, for each input, we should send the arrow just once, okay? Not less than once or no more than once, right? So 0 arrow or maybe more than 1 arrows, yeah, will violate the kind of constraint of a function, okay? Okay, so in this case, so let me make it as a valid function like this, okay? So in this case, let's study a few terms used in the world of a function. So this is a function, and so we consider this kind of set that contains every input that we can use in our function. So what was it called? What was it called in Korean? Yeah, in Korean. 뭐라 그랬죠? 그렇죠? What's it in English? It's domain. Okay, domain. And then, so this one is called what? 한글로 뭐라 그러죠? 공역이라고 부르죠. So that is called codomain. Okay, so that is the English name, codomain. Okay, and then the actual target that got hit by at least one arrow, in this case 6, 7, 8. So that is called 시역이라고 부르죠. 이건 뭐라 그럴까요? 잘하는데요? 벡터도 안 배우고 이런 거 어디서 배웠어? So it's called a range. Okay. Okay, so of course this range is actually a subset of these codomain, right? So it is range is basically a subset of the codomain, and it can be either the same or can be strictly smaller than the codomain, right? So in this case, is it possible that this range is the same as codomain? So again, in other words, can we make the range to be the same as codomain? Is it possible? So in this particular case, 어떨 것 같다고요? 네, 가능할 것 같아. 어떻게? 불황식을 없애면? 네. 불황식을 없애면 그렇죠. 뭐 큰 거를 더 작게 만들면 되긴 하는데. Okay, so let's assume that at least codomain is fixed as 5, 6, 7, 8, 9, 10. So in this case, that range cannot be the same as codomain, and the reason is because we have actually smaller number of elements in our domain, right? Because we have only 4 input elements, so we have 4 arrows, right? 4 bullets in our gun, right? And then we have a 6 target, right? 5, 6, 7, 8, 9, 10. So 6 targets. So using 4 bullets, we cannot shoot all of them, right? So that in that case, range, cannot be the same as codomain. And we will study this kind of property at the end of the next chapter of a 1.9. So let's keep that really well in mind. Okay, but anyways, so we studied the domain, codomain, and range, and then so there is another last term that we need to study, which is like an image. An image is simply like function output. So function output of a particular x value. Okay, function output of a particular x value. So let's define or call it as an f, and f2 is what? 7, right? Because the target is 7. So in this case, the image of 2 is 7, okay? Or in other words, the function output of 2 is 7, okay? So image is simply the function output of a particular x value. So x should be given as a particular value, okay? So the collection of all the possible images, right? So that is also called a span, right? Span is like the bigger set when using all the possible x values, right? Okay, so we studied a few terms, And then because in this class we are studying like vectors or matrices and so on, we consider the function that maps some vector into some other vector. So we are considering the vector, so we are considering the function that handles the vector. Okay, so our domain is some vector space and the output is another vector space. So let's think about some vector space as maybe Rm and this one as Rn. Okay, so for example, we can at least think about like this kind of example where the function sends like three-dimensional vector. For example, 1 to 3 was sent to or mapped into like 4 or 5, which is one of the two-dimensional vector. Okay, so we consider this kind of function that maps a particular particular vector in a particular dimension, which is called M, and then it sends this vector into some other vector which lives in like this another dimensional space. So in this case, the domain is Rm and the codomain is Rn, right? And then we want to represent this function as a matrix vector multiplication. So let's think about this vector as an x and this one as y, and then we want to represent this function as a times x. Okay, a is our matrix and x is our input vector, which is our three-dimensional vector. So in this case, let me ask this question. So in this particular case where m is 3 and n is 2, what should be the size of the matrix A? What should be the size? What is the size? 2 by 3 or 3 by 2? Yeah. Okay, great. Yeah, A should be 2 by 3 because we will multiply x, column vector x on the right, right? And then that will produce these two-dimensional vector. Okay? So in this case, if the matrix size is m by n, okay, so let me just write it as n and m. Okay, so in this case, our domain is n-dimensional space, and the codomain it will be m-dimensional space. And if A is m by n, okay, so this m will be the dimension of the codomain, and this one will be the dimension of the domain or x input. Okay, so so far so good. Okay, so let's look at this example where A is given as this matrix and U and B as these two vectors. So A is 3 by 2, so it sends like two-dimensional vector into three-dimensional vector, right? Okay, and then our function definition will be represented as A times x, and then it will be represented in this form, right? We are just simply doing this inner product to represent the first, second, and the third entry. Okay, so in this case, so let's think about these 4 different problems, which are quite simple. So find the t of u. So image of t, or function output or function value of the vector u under the transformation of t. Okay, so in this case, so t is defined here, and then t of u is just simply obtained by just plugging this guy into this part. Okay, we can just this matrix vector multiplication, and that is quite simple. And then let's move on to the next one. Find an x whose image under T is B. So in this case, the question is, we do not know the input vector x, but we know that the function output or the image should be this vector 3, 2, and -5. So yeah, so in this case it's quite simple because we are, let's see, yeah, we are trying to solve this linear system. So a times x, and then it will be the given function output or given image as 3 and 2 -5. And in this case, what will be x1 and x2, right? In that case, it is exactly having the form of ax equals b, which is our linear system. And then in order to solve it, we will just do this row reduction, right? So by doing this row reduction, we can obtain this vector x, or the input value that will shoot the arrow to the 3, 2, -5. Okay, so let's move on to the third one. What was the third one? Is there more than one x whose image under T is B? Okay, so we still consider the same B, 3, 2, and -5. And then here the question is, in terms of the input element or input vector that has the function output as 3, 2, -5, okay, is this input vector just only one, or are there more than one possible vector x? Okay. So given this linear system, okay, so that question is the same as whether we have more than one solution or not in this particular linear system, right? So that is the third question. And in that case, by looking at this reduced echelon form, we can see that we have no free variable, right? And thus, the solution will be only one. So we will have just one solution, and thus the question here, the answer for the third question is no, right? And in this case, it is actually the same as, okay, so let's think about this case. In this particular function mapping, let's think of the same problem in this example. So we are given the function output or the image of a function as a particular value, and then in this case, is there any, is there more than one possible x values that satisfies this? So in this case, who is shooting the arrow to 8? It is shooting the, it is 3 that shoots the arrow, right? So there is only one element, so x will be 3. But in terms of the number of x values that will shoot the arrow into 8, so we have only one input value in this particular case, right? Right. So in this case, we will only have one element. But what about this case, fx equals 7? So in this case, to 7, these 2 and 3 are shooting the arrows, right? So in this case, the total number of input values that will be mapped into the same value of 7 is not 2 and 3, but 2 and 4. So in this case, more than one input value will shoot the arrow into the same target value, right? So we consider this kind of situation, okay? And that situation is determined by checking this reduced echelon form. Okay, this reduced echelon form. And then here in this case, back to this question of an AX equals B. So our assumption is B is already given. So B is given as a particular constant vector that is known. And in this case, the question is, do we have an more than one solution for this X that satisfies this equation, or do we have only one vector X that satisfies this? Okay, so that problem is actually the same as whether we have a free variable or not in the matrix X, matrix A, right? So in this function, the number of X vectors that is mapped into the same vector or same target vector or same target image vector. So that is determined based on whether we have a free variable or not. Okay. So still we are handling this the same problem by using the free variable or like linearly dependence or independence relationships. Okay, so in this case, because we have no free variable, and thus, is there more than one solution? The answer is no. Okay, so let's look at the first problem. Determine whether C is in the range of the transformation T. So what was T? What was C? There is no C. Okay, so in this case, it looks like the C was 3, 2, non-negative 5, but the 3 and 2 and 5. Okay, suppose let's consider this 3, 2, and 5. And in this case, let's try to find out this AX equals B so that we can find the input vector X that shoots the arrow into 3, 2, 5. So in this case, this is our echelon form, and then we can find the pivot on the rightmost column. So in this case, we can conclude that we have no solution at all, right? So in this case, there exists no X vector that maps or that shoots the arrow into this vector. Okay, so what does that mean? So that means, so in this case, we are shooting the arrow. Let's consider the domain and the codomain. So what was the original matrix A? Matrix A was this, right? So it is having the domain as 2-dimensional space and the codomain as the 3-dimensional space, right? So in this case, so this is codomain, and then we can think of the range of our function or this transformation, and 3, 2, 5. Although this one belongs to our codomain, but this one is not belonging to our range of this function. Okay, maybe this function st, because that is, no one shoots the arrow into 3, 2, 5, right? So this one is clearly outside of this range. Okay, and then this 3, 2, 5 is corresponding to the elements like 9 or 10. Okay. And also in this case, this range is strictly smaller than the codomain, right? Okay. And in this case, what will be our range actually? So let's just think about the range directly given this matrix. So what is the range? So we will use any possible input vector X, which is our 2-dimensional vector, X1 and X2, right? So we just freely set any values for these x1 and x2, right? And because that will be like input vector in our domain, right? So we freely choose these vector x, which is a two-dimensional vector, and then the range will be the function output that is formed in this shape, a times x, right? And then a times x is actually, yeah, we studied that these are the linear combination of these two vectors, right? These two vectors by using the linear combination coefficient of an x1 and x2, right? And then what is our codomain again? The codomain is three-dimensional space, right? And then our range is actually the linear combination of these two vectors, two column vectors, or here in this case, the range is what? It's just the same as the span of the two vectors, right? 1, 3, -1, -3, 5, 7. So we have these two vectors, and then their span is actually the same as the range, okay? And then in this case, we are considering the three-dimensional space as a codomain, and then we only have like two-dimensional vector. Two vectors, right? The first one is 1, 3, 1, and 1, 3, -1, then -3, 5, 7. So we only have two vectors in the three-dimensional space, and then their span will be like this thin plane, right? And that doesn't cover the entire three-dimensional space, right? Three-dimensional space is our codomain, and this thin plane will be our range defined by this function or this transformation, right? And also you can think of this situation a little bit more intuitively, but not mathematically. But yeah, let me also describe that way as well. So we are doing the mapping from the two-dimensional vector into three-dimensional vector. So let's think about the number of elements in our domain and the codomain. So the domain, I mean the total number of input elements in our domain is actually living in the two-dimensional space. So we are collecting all the possible points in the two-dimensional space. But our codomain, yeah, so in our codomain, we will have those points that we pick up in the three-dimensional space. So in terms of the number of points, number of elements, which one will have a larger number of elements? So intuitively, like the two-dimensional space, the total number of points will be much smaller than the three-dimensional, the total number of points in the three-dimensional space, right? Because three-dimensional space is much bigger. We cannot give a exact count or exact number of points living in the two-dimensional space, and also like the three-dimensional space, because both of them will have an infinite number of points, right? Because we are considering continuous values, right? But still, like between different infinity values, we can still consider which one is a larger infinity or smaller infinity, yeah, something like that, right? So in this case, the total number of points in the three-dimensional space is much larger than the two-dimensional space, and thus that is actually the same as the case like this, okay? So in this case, so why didn't we have the same, why was it not possible that this range to be the same as the codomain? It is because we simply have only 4 elements, but in our codomain, we have actually more number of elements in our codomain, right? So we have 6 elements, and thus, again, we have 4 bullets in total. So we can only shoot up to 4 elements in our codomain, and thus there will be always like those elements that are not get shooted by those input elements in our domain, right? So this is exactly the case like the mapping from two-dimensional into three-dimensional case. Okay, and that, yeah, so that is kind of an intuitive understanding, not really mathematically, but we can also, yeah, understand mathematically by using these span of these column vectors given in this matrix A. Okay. So what about this case, in like the opposite case, R3 into R2? So in this case, the input vector is multiplied on the right, and thus our transformation matrix will be 2 by 3. So in this case, we have, so in this case, the range will still be the same as span of these three vectors, right? The range will be the span of these three vectors, right? Because we can freely choose any vector x as our input vector, because our domain is entire three-dimensional space, right? So in this case, we have three vectors. So suppose these three vectors are like the first, in this two-dimensional space, the first one, and the second one, and the third one. In this case, the span of these three vectors will cover the entire two-dimensional space. So in that case, the range will be the same as codomain, right? Okay, so because I started to discuss this, let's go to chapter 1.9 and then just address or understand what this is about. So this is about this thing, onto and one-to-one. Onto and one-to-one. So this red one, so onto. So this one will be, for sure, it will be given or included in your exam, and also, of course, you will do some exercise by solving some homework problems. Yeah, but this onto means, so this is the situation where this range is the same as codomain. Okay, so onto means the range is the same as codomain. Okay, so what does that mean? What does that mean? Given the vector mapping from Rn into Rm, so what is range? What is codomain? It's the Rm, right? So Rm, and then what is the range? What is the range? The range, if our vector f is represented as A times x, which is our matrix times vector multiplication, and in that case, the range is the span of the columns of A. Okay, so sorry for poor handwriting, but the range of this function A times x is the same as the span of the columns of an A. Okay, so that span is the same as the codomain or the entire universe of Rm, and then that's when your function is onto. Okay, so this one is this is when this your function is onto. Okay, and then also it can be represented in this statement. So every B in the codomain space. So in your codomain space, so let's think about three-dimensional into two-dimensional space. So in our two-dimensional space, which is our codomain, we pick up any vector B. Okay, so let's pick up any vector, like any two-dimensional vector, as maybe 3, 5. Okay, so you picked up arbitrary vector in the two-dimensional space, and then this vector is an image, okay, is an image of at least one x. So that means this function value will get hit by at least one kind of input vector. So it gets hit by this arrow at least once. Okay, and that means if that element got hit at least once by this arrow, and then it means that this entry is belonging to our range, right? And so for whatever vector, whatever two-dimensional vector you choose, and then that vector is that vector got hit by at least one arrow, and that means your range is the same as codomain, right? So that is another statement or description of the situation where this range is the same as codomain, okay? And that is actually the same as this R2 is fully spanned by your columns of an A. So that is onto. Okay, and then let's think about the another one. This 1 to 1. Okay, 1 to 1. So 1 to 1 is 네, 이거 한글로 뭐라 그러죠? 1 to 1. 1대1 두 가지가 있었어요. 1대1 함수랑 1대1 대응이라. 그죠? 아마 네, 내가 기억한 게 맞다면 하여튼 두 개 다르죠? 1대1 대응이랑 1대1 함수랑 1대1 네, 이건 그래서 1대1 함수가 돼요. 1대1 함수. Okay, so this one-to-one, yeah, let me describe it. So in this one-to-one case, you don't need to satisfy this constraint. I mean, so you don't need to satisfy this requirement, which corresponds to our onto requirement, right? So we are talking about the different requirement or property of one-to-one, and this one-to-one is first considering the range. Okay, so it considers the range, and then you pick up any vector in your range, not from the codomain. Okay, so in this case, your range is okay even if it is strictly smaller than the codomain. Okay, but when looking at this range and then picking up any values in the range and consider which one actually shoots the arrow to that particular element in your range, and then that arrow should be that there should be only one arrow for each of your element in the range. So that is called the one-to-one or 1대1 함수. Okay, so that means for each entry in your range, you should be able to always find one unique vector x that shoots the arrow to that particular output value in the range. Okay, so that is called the one-to-one. Okay, so let's think about this case. Is this one-to-one or not? Eh? So this is not, right? In this case, let's check in detail. So we only consider the range. We do not consider the codomain. Okay? So the range will be 6, 7, 8. Right? 6, 7, 8. In this case, we check every element, each element, and then whether each of these entry got hit by only one arrow. Okay, so that is the requirement for one-to-one. But in this case, 6 and 8 were okay, but 7, in the case of 7, it got hit by 2 arrows. So in this case, it is not one-to-one, right? So you got the you understand the definition of one-to-one, right? Okay, and then now let's think about the the vector transformation between the vectors. Okay, so which is defined by defined by the matrix vector multiplication like this. Okay, so let's consider the matrix A as having like 3 different columns. So 3 different columns, and then our vector x will be x1, x2, and x3. Okay, so what is the range? So range is the span of these 3 vectors, right? So we already learned that, right? And then we pick up any vector in our range, which is the span. Which is a one vector belonging to that span. Okay. Then suppose that vector, with maybe that vector is placed on the right hand side, and then consider ax equals b. Okay. So here the question is, vector x, is there a unique vector x, or can we find multiple different vector x, or is there more than one possible vector x that satisfies that linear system? Okay, so that is actually the same as 1 to 1 in this transformation of matrix times vector multiplication. So in order to determine whether this function is 1 to 1 or not, what kind of properties should we look at, or should we check? So again, we are concerning, or we want to try to answer the problem of whether we have unique solution or infinitely many solutions. Right? So what does it correspond to? 뭐랑 그럼 연결이 되죠? 이게 네? 뭐랑 연결이 되죠? 해가 하나냐 아니면 무한이 맞냐? 이거 뭐였어요? 네? Free variable. Okay. So if we have a free variable, and then this one will have an infinitely many solution, and that means from the perspective of a function or transformation, it actually shoots multiple arrows into the same entry, same output in the codomain, in the range. Okay. So if we have a free variable, and then the function is not 1 to 1. If we don't have a free variable, and then function is 1 to 1. Okay. So again, the free variable, if we have a free variable, and then the function is not 1 to 1, because we can find the multiple different x inputs that shoots the arrow into the same function output b. Okay, but if we don't have a free variable, and then this is when the function is 1 to 1. Okay, and then let's think about this case where we have the mapping from 3-dimensional space into like 2-dimensional space, R3 into R2. Or let me just start with this simple case. So in this particular case, I want you to think about the number of elements. The count of these elements in our domain and the codomain. So in this case, so we have a more number of elements in our codomain than the number of elements in the domain. So in this case, it is not possible to achieve onto, right? Because in this case, range should be strictly smaller than the codomain, right? So this one will clearly not satisfy the onto, right? But what about the 1 to 1? Although in this case it is not satisfying the 1 to 1, can we think of the mapping that satisfies 1 to 1? Yep, I think the answer is yes, because like this guy, and then maybe this guy, and then this guy. Okay, so in this case, the the range is now 5, 6, 7, 8, right? And then each entry got hit only once by the input, right? So in this case, it is clearly a one-to-one mapping, right? So this is one-to-one, right? And in this case, so we can think of the kind of necessary condition to satisfy this one-to-one. So in this case, what if we have like 1, 2, 3, 4, 5, 6, 7? So in this case, is it possible to achieve one-to-one in this case? So it is not, right? Because we only have 3 entries in our codomain, but we have 4 elements in our domain. And so the requirement of a function is that each entry in our domain should shoot the arrow just once, right? No less than once or no more than once, right? So in this case, we at least shoot the 4 bullets or 4 arrows, but we only have like 3 targets, and thus at least one of them will get hit multiple times, right? Okay, so let's bring that kind of concept or understanding into our vector space. So in this case, where we map an input vector, 3-dimensional input vector into 2-dimensional input vector. So in that case, our input domain is like this kind of 3-dimensional space. And then our codomain is only like very thin 2-dimensional space. So which set contains more number of elements. Clearly, like this guy will have more number of elements. So in this case, it is not possible to achieve one-to-one, right? And then let's just mathematically prove that, or let's understand it mathematically. Yeah. So in this case, what will be the shape of our function? So in this case, it's like the input vector is 3-dimensional space, and then so our matrix will have 2 by 3, right? So in this case, we have 3 vectors, right? 3 vectors. Okay, so in this case, suppose you picked up one element from the range. Okay, suppose you picked up the one element from the range. That means again the range, so again the range is these 3 2-dimensional 3 vectors, right? Span of these 3 vectors will be our range. And then suppose you picked up one element there, and then suppose that is this 2-dimensional vector. And clearly, because we picked up this element from our range, it will have at least one solution, right? Because we picked up the element from the range, right? Not outside of the range, right? And then that element will clearly be represented as a linear combination of these 3 vectors because it's inside of our span, right? But here the question is whether this linear system of AX equals B have a unique solution or infinitely many solutions. Okay. So if we can find a unique solution, and then that's corresponding to the onto case. But if we can find the infinitely many solution, and then this is when we cannot achieve we cannot achieve one-to-one, right? We cannot achieve one-to-one in this case if we have a infinitely many or more than one solution. And in this case, so we have a 3 vectors, and then they are living in the 2-dimensional space. And so, so in this case, we will at least have one free variable, right? Because we have 3 vectors in the 2-dimensional space, right? And so adding one vector at a time, eventually, one of them should be linearly dependent, or one of them should be represented as a linear combination of the previous vector, right? So, so that way, so we always have the free variable in this case, and that means, so we cannot achieve one-to-one. Okay. So again, yeah, we can also confirm that one-to-one is the same as having no free variable. So one-to-one is no free variable, the same as no free variable, but not one-to-one is the same as having free variable, or at least one free variable. Okay, so that's how all these things are connected with each other. So that was a one-to-one. Okay, then so let's think about this as 3 by 4. So in this case, it's mapping the vector from mapping the three-dimensional vector into four-dimensional vector into three-dimensional vector. Is this one-to-one? So one-to-one is we have to check the whether we have a free variable or not. So we have a four vectors in the three-dimensional space. So we should have at least one free variable, right? In other words, they should be linearly dependent, right? And thus, you cannot achieve one-to-one, right? So even before changing it into echelon form, we can immediately answer that, right? But what if what about the onto? Is it possible to achieve onto? Let me see. Okay, so onto means the span of these 4 columns should be the same as the entire three-dimensional space or our codomain, right? So we have to check that, right? And that is the same as checking, after changing it into the echelon form, and then suppose our echelon form is something like this. So we still have the, this is a coefficient matrix. So it's like this. Okay, so in this case, this is when adding one vector at a time. So the first vector and the second vector is up to these two linearly dependent, right? And then what about the third vector? So the third vector is actually our free variable, and that's when this third vector is represented as a linear combination of the previous ones, right? So we studied that right last time. And then the fourth vector will also have a pivot, and then the fourth vector is something like this, and thus at least in this case, we will span the entire three-dimensional space by using the 4 vectors. In this case, it is onto, right? But it is not always onto in case where we have I need to, oops. Something like this, okay? So in this case, first vector, and then second vector doesn't have a pivot, and thus it will be something like this, right? It will be represented as a linear combination coefficient, linear combination of the previous vector, and then the second vector is something like this, and that will increase the span, and then the fourth vector is doesn't contain the span, doesn't contain the pivot, and thus that the fourth vector is contained or belonging to the span of the previous one. So overall, in this case, that doesn't span the entire three-dimensional space. So even if we have a 4 vector, so 4 vector span is just just like this, right? Okay, so not this one. So still, the span will be thin plane in the three-dimensional space, and thus in this case, range is strictly smaller than the codomain, right? So it doesn't fully span the three-dimensional space. So this one is not onto. So even if we are mapping like four-dimensional vectors into three-dimensional vectors, which is a smaller number of an entry or elements in our codomain, yeah, it is not always the case that our function is onto. So it may or may not be onto in this case. We have to actually check that echelon form and the pivot position. Okay, so yeah, that's it for today. And so today is Tuesday. Okay, so let's meet next this Thursday. Thank you.
그러면은
네.
코드 A의 그 차원이 더 적으면은 무조건 A는 리니어리 디펜던트라고 할 수
그렇죠. 네.
있어요.
네, 매트릭스 쉐입이 이렇게 좀 옆으로 길쭉하잖아요. 이쪽이 더 디멘전이 크니까.
네네.
그러니까 이게 기본적으로 여기 차원이 뭐 3이면 여기가 3보다 더 많은, 그러니까 3차원에서 벡터 개수, 주어진 벡터 개수는 3보다 더 큰 뭐 4개 혹은 그 이상인 거예요. 그러면 리니어리 디펜던트 하니까 그래서 이제 원투원도 안 되는 거예요.
오늘 전반적으로 잘 이해가 안 된 것 같아요.
아, 그래요?
네, 예를 들어 R3 이제 R2로 보낸다는 거는 정의역이 3개인 경우에 치역이 2개인 경우로 치역이란다 공역.
아니에요. 그러니까 3차원 벡터를 2차원으로 보낸다는 뜻이지
네.
정의역의 어떤 원소의 개수가 3개라는 뜻이 아니거든요.
근데 처음에 함수 관점에서 생각하면 이거는
네. 함수 관점에서 이렇게 하나의 예를 드는 거고요.
네.
우리가 이제 R2에서 R3가 된다. 그러면 예를 들면 여기에 이제 우리가 이렇게 두 개를 자유롭게 조절할 때랑
네.
여기에 이렇게 자유롭게 이렇게 될 때랑, 그러니까 우리의 정의역은 이 2디멘sional 벡터를 자유롭게 우리가 조절할 때 그 모든 엔트리를 다 우리의 정의역이라고 하는 거예요.
네.
그 엔트리를 다 모았을 때. 그러니까 기본적으로 이거는 정의역 자체가 이제 그 정의역의 원소의 개수가 무수히 많은 거예요.
네.
맞죠?
네.
이것도 역시 3디멘sional 벡터도 역시 개수가 무수히 많아요.
치역의 개수가.
일단은 그렇죠. 치역도 그런데 공역이 일단은 공역이 이제 무수히 많죠.
네. 공역.
네.
근데 1대1 함수 이거 관점, 그러니까 1대1 함수가 될 수 있는지 아닌지, 이런 경우에 1대1 대응이 절대 될 수 없다 했을 때 약간 함수 관점에서 봤잖아요. 그러니까
네.
함수 관점에서 제가 이해했을 때는 AX는 B 했을 때
네.
이게 함수를 변환시키는, 그러니까 F 기능하는 거고,
네,
X가
그렇죠.
정의역,
맞아요.
B가 공역 또는 치.
네, 그렇죠. 그러니까 일단은 B가 살고 있는 스페이스가 3차원이다 그러면
네.
이 3차원을 우리가 일단은 공역으로 놓고요.
그래서 될 수 있는 값이 치역이 되는 거예요.
그렇죠.
공역 중에.
네.
근데 그러면 그까지 이해했으면 이제 1대1 대응이 아니다가 되는 조건이
1대1 함수가 아니다?
네, 1대1
네.
함수가 아니다라는 게 해가 유니크하다는 말이 곧 1대1 함수다라는 말이 됐는데,
네, 맞아요.
어떻게 그렇게 되는지.
그러니까 이제 치역에서 원소란 치역에서 원소를 하나를 고르면
네.
이제 AX라는 펑션이 있을 때 치역에서 하나를 골랐어요. 그래서 그 원소가 B라는 벡터라고 한다면 이 B라는 벡터에 화살을 누가 쏘느냐, 이 X가 이제 화살을 쏘는데 화살을 쏘는 애가 하나밖에 없다 라고 하면 이게 1대1 함수고요.
그러면 이제 이렇게 아까 예시로든 2 곱하기 3 모양의
네.
2 곱하기 1을 해서 2 곱하기 1 되는, 그러니까 얘가 치역을 공역을 범위고 얘가 정의역을 범위를.
그렇죠. 네. 그러니까 2 곱하기 3 이런 거.
네, 그게 A고 이제 이게 X고.
네.
했을 때 만약에 이제 말씀하신 대로 여기
네.
치역이 하나 정해진 값, 답이 될 수 있는 값 4, 5가
네.
왔다
하나
했을
오면
때
네.
쏠 수 있는 게 이제 1, 2, 3 얘만 이쪽으로 유니크하게 단일하게 쏠 수 있고,
그렇죠.
다른 값이 못
네.
오면.
그러니까 이게 이 전체 벡터 하나가 얘한테 쏘는 거예요, 화살을. 그리고 또 다른 3차원 벡터 하나가 또 얘한테 쏠 수 있을 때,
네.
쏘고 있을 때 이제 그게 이제 원투원이 안 되는 거예요.
그러면 이제 1, 2, 3이 4, 5로 가고
네.
만약에 다른 값 4, 6이 됐을 때 1, 2, 4가 이제 x가 달라진 값이고 얘도 그 y가 달라진 값인데 이렇게 써도 1대1 대응이 되잖아요.
1대1 함수가 돼요. 네. 그러니까 우리는 치역의 모든 원소들을 다 체크해야 돼요. 이것도 체크해야 되고 이것도 체크해야 되거든요. 그래서 얘한테 쏜 화살을 쏜 애가 하나, 얘한테 화살을 쏜 애가 하나. 이제 하나씩만 있어야 되고
네.
이게 근데 뭐 이게 치역에 있는 이 저기 벡터를 모든 애들을 다 우리가 체크를 할 수는 없고요.
네.
이게 중요한 건 일단 여기서 치역에서 하나를 골랐어요. 여기. 그러면은 이게 뭔지 일단 보기 전에 일단 치역에서 골랐다는 거는 이 세 개의 컬럼의 스팬 안에 들어와 있다는 뜻이고요.
근데 거기서 치역에서 하나 골랐다는 의미가 이제 x, y로 놨을 때
네.
치역에서 하나 골랐다는 게 치역이 될 수 있는 게 4, 2, 6, 9일.
4, 6이 이게 벡터 하나가 원소예요. 4랑 6이 따로가 아니라.
그러면 이제 fx 관점에서 봤을 때 x에 그냥 하나가 오는 게 아니라 그냥 예를 들어
그러니까 우리는 그러니까 원소 하나는 벡터예요, 지금. 1이 뭐 몇으로, 2가 몇으로 가는 게 아니라, 그건 아까 예를 들어서 내가 이야기했던 거, 그거는 그러니까 R1에서 R1으로 가는 케이스예요.
그 함수 정의역도 벡터고
네,
치역 공격
그렇죠,
다
그렇죠.
벡터.
네, 맞아요.
자꾸 단일 원소를.
그러니까 그게.
감사합니다.
네.
아까 질문드린
네.
것처럼
그거 시험 문제?
네?
시험 문제? 아니, 시험이
아니, 시험이 과제
숙제 문제?
아니 그 자체가 이해가 안 되니까요.
네.
그러니까 국제에서 번 돈을 다시
그-
국제인 서비스로 보내는 건데
네.
이거를
내가 문제를 지금 문제를 기억을 못 해갖고, 네, 잠깐만요. 내가 책을 한번 좀 보고.
챕터 1-6을 넘어가셨죠?
네, 챕터 1-6은 안 해요.
저 꺼도 되나요?
네.
과제랑은 과제는 있어가지고 책으로 다시
1-6이 과제 있어요?
1-6이 과제 있어요.
과제 있어요? 1-6이?
네?
그래요? 그거 잘못 냈네요. 빼줄게요. 그거 1-6이었어요?
네네.
그러게요. 그거 빼줄게요.
무슨 질문 있습니다.
이제 그 피벗 포지션의 정의 자체는 기약 사다리꼴 행렬을 가지고 하잖아요. 그러니까 책에는 그렇게 나와 있는데 솔직히 사다리꼴 행렬까지만 만들어 어디가 피벗이겠구나 감은 오잖아요. 그 상태에서 바로 한 대충 사다리꼴만 만들어 놓은 다음에 뭐 예를 들어서 뭐 이 각 컬럼들이 뭐 R4를 스팬하냐 뭐 그런 문제가 있을 때 대충 사다리꼴만 만들어 놓고 딱 봐도 피벗이 3개밖에 없네 뭐 이런 식으로 진행을 해도 크게 논리가 막
그렇죠. 네. 피벗이 어디 있는지만 알면
네.
사실 우리가 하는 뭐 리니얼리 인디펜던트냐 디펜던트냐 뭐 원투원이냐 뭐 이런 것들 온투냐 이런 것들이
네.
그냥 거의 다 풀려요.
그러니까 굳이 그거를 REF까지 끌고 갈 필요가 없어.
RREF?
네.
리듀스 에이션
네네.
로 네, 맞아요. 네.
그렇죠. 알겠습니다.
리듀스 에이션 로까지만 가면 돼요. 알겠습니다.
아까 그 예시로 설명된
네.
부분 좀 더 봐줄 수 있을까요? 앞에 단어였던 것 같은데. 아닌가? 잠시만요.
매트릭스 갖고 한 거요?
네네네.
그러면 여기나 요건가요 혹시?
아까 그 수업 자료.
수업 자료?
네 그냥 여기서
그래요?
네 이거 몇 단위였는지 정확히 기억 안
한번 찾아볼래요 그럼?
네.
천천히 한번 찾아보세요.
그러니까 여기 있잖아요.
네.
그러니까 여기서 리듀스드 에실론 폼으로 바꾸면
네.
그 맨 밑에 000이 나오긴 했는데
네.
이거는 변수의 개수보다 랑 상관이 없어서 프리베리어블이 아닌 건가요? 그러니까 x3이 없으니까 이게 원래라면
네. 그러니까 이게 지금 어그멘티드 매트릭스잖아요.
네네
그리고 이게 베리어블 1번, 2번 베리어블이고요.
네.
그 다음에 각각 피벗이 있으니까
네네
일단 얘네들은 다 베이직
네,
베리어블이고
그러니까 x1에 배운되고 x2에 배운되는
그렇죠.
거잖아요. 그러니까 요 밑에 거는 신경을 쓸 필요가 없는 거예요.
밑에 거는 지금 네, 이 경우는 그러니까 우리가 그 전에 배웠던 것 중에 이제 이 로우가 그러니까 이 코에피션트 매트릭스만을 가지고
네.
로우의 모든 로우들의 피벗이 있냐 없냐 측면에서 보면 없잖아요. 여기에
네.
마지막에 피벗이 없죠.
네네.
마지막 로우에는 피벗이 없죠.
네.
그러다 보니까 이 경우는 어떤 경우냐면 이 두 개의 혹은 우리한테 주어진 이 컬럼 벡터들이
네.
우리의 전체 스페이스를 다 그 커버를 못하는 거예요. 그러니까 3차원 스페이스고 얘네들이 살고 있는
네네.
벡터는 뭐 두 개밖에 없으니까 커버를 못하고 있죠.
네.
그러니까 이 경우는 이 두 개의 벡터의 스팬이 전체 3차원을 다 뒤덮지를 못하고 있고 그런 말, 그 말은 이 주어진 이 B가 어떤 벡터냐에 따라서
네.
어떤 벡터냐에 따라서 해가 있을 수 있고 없을 수 있어요.
아, 네.
그렇죠? 근데 이 특정 3, 2, 마이너스 5의 경우에는 이게 운이 좋게 다행히 네, 해가 이렇게 있는 거예요.
네.
왜냐하면 하여튼 해가 없다? 그러니까 마지막에 여기에 이제 피벗이 나타나면 이때가 0, 0 이게 해가 없는 건데 여기가 다행히 같이 0이 됐잖아요.
네.
그러니까 얘는 이제 해가 있는 애인 거예요.
아, 네.
네. 그러면 그 해가 지금 중요한 건 해가 있긴 있는데 그 해가 하나냐 아니면 여러 개냐를 따지는 거예요. 근데 여기서는 지금 네, 베이직 베리어블만 있고 프리 베리어블은 없으니까 해가 하나만 있는 거죠. 유니크하게.
덕질을 못하면
네.
그게 온투가 안 되는 거죠. 그러면.
그렇죠. 이 경우는 온투가 안 되는 거예요. 그러니까.
아, 근데 여기서 또
네.
보면은 이게 마이너스 35가 나타났잖아요.
네, 이거는 그러니까 레인지 있지 못한 거죠.
근데 지금 뭐지? 여기도 근데 x1, x2만 있는 거잖아요.
응?
그러니까 2차원 벡터에서 3차원 벡터로
3차원으로 가는 거죠.
가는 건데
네.
그러면은 벡터 안에는 엔트리가 2개밖에 없잖아요.
네.
근데 그러면은 이 위에만 사실 그 해를 구하는데 관여되는 거 아닌가요?
이 위? 얘네?
네, 그러니까 이렇게 두 줄.
이렇게 두 줄이요?
아니, 이렇게.
네, 이렇게 두 줄?
2로하고 2로야. 네.
아, 그렇지는 않아요. 왜냐면 이게 이거 리니어 시스템을 생각해보면 여기다가
네.
여기다가 이제 여기다가 x1, x2 이렇게 해갖고
네.
이게 3, 2 어쩌고 나와야 돼, 뭐 이게 나와야 되는 거잖아요.
네.
그러니까 이거는 지금 이 두 개의 컬럼의 리니어 컨비네이션을 잘 조합을 해서
네.
이 최종 컬럼을 만들어내야 되는 거예요. 지금 우리가 만족해야 되는 이퀘이션은 3개인 거는 여전히 동일해요.
아,
그렇지만 미지수가 2개밖에 없는 거죠.
아, 미지수의 개수랑 그럼 그거
방정식의
이퀘이션
개수나,
개수가 또
네.
다른 별개네요.
그렇죠.
그러니까 여기서 맨 마지막 줄이니까 미지수의 개수가 2개인데
네.
이퀘이션이 3개면
네, 그러니까 이거는 마지막 이퀘이션을 이거는 만족을 못 시키는 경우.
아, 그러니까 0인 거는 상관없는 피벗이
그렇죠.
안 나타나는 게 피벗이
네.
나타났기 때문에
그렇죠. 네. 그러니까 그거는 우리가 미지수 2개만으로는 아까 얘기했던 것처럼 이 컬럼을 아무리 조합을 해도 마지막 엔트리만 우리가 이렇게 집중해서 보면
네.
걔만 신경 써서 본다면 0, 0을 아무리 조합해도 0이거든요.
네.
그러니까 이 어떤 0이 아닌 값을 우리는 만들 수가 없기 때문에 이게 해가 어떻게 해도 없는 거예요.
그리고 스팬이라는 게 정확히 어떤 의미인가요?
스팬이요?
네.
그러니까 주어진 어떤 벡터가 있어요. 1, 2, 3,
네.
4, 5, 6이라는 벡터가 주어져 있으면
네.
이 두 개를 가지고 우리가 쫙쫙 그렇게 펼쳐갖고 만들 수 있는 그게 스팬이고
그 범위.
네, 이 두 개를 가지고 이걸
네.
쭉 뭐 아무렇게나 막 늘려갖고
네.
거기에서 만들어지는 평행사 변형의 그 꼭지점을 따져서 그 꼭지점들의 모든 집합, 그렇죠. 꼭지점으로 만들어질 수 있는 가능한 모든 점들의 집합을 스팬이라고 표현을 해요.
그 스팬이 치역인 거죠. 공간 내에 있는
네,
치역.
그렇죠. 네.
그러면은 그 아까 말했듯이 여기서 그러니까 차원 뭐라고 해야 되지? 도메인 벡터의 차원이 코도메인 벡터
네.
차원보다 더 클 경우가 있었잖아요. 그러니까
네.
3에서 2로 갈 경우나
네, 네, 네.
그럴 경우에는
네.
그냥 스팬이 다 커버를 하는 거죠.
그럴 수도 있고 아닐 수 있어요.
아닐 수도 있어요.
그러니까 예를 들면 벡터 3개가 이렇게 있어요.
네.
한 라인으로 다 있어요. 1, 2, 2, 4, 3, 6 이러면
네.
이러면 보면 결국 벡터는 3개 주어져서 뭐 지금 차원이 2차원이니까 벡터가 3개니까 더 차원 수보다 많아서 전체를 다 뒤덮을 것 같지만 스팬이 다 뒤덮을 것 같지만 지금 이거는 3개 벡터가 결국 다 한 라인에 있다라는
반드시
거는
그렇지 않을 수도 있고.
반드시 그렇지는 않을 수 있어서
한 라인에
피벗을
있어서.
체크를 해봐야 돼요.
네.
네.
근데 원투원은 무조건 아니라고 했다. 그러니까
원투원은
프리베리어블 무조건
그렇죠.
나와요.
네. 프리베리어블. 네.
아니 알겠습니다.
네. 잘 좀 복습 좀 해보세요. 정리만 좀 하면 뭐 굉장히 클리어한데 이게 헷갈리기 시작하면 이게 저건가 저게 이건가 막 이래서. 네. 네, 수고했어요.
빠르게 두 가지만
네.
여쭤보도록 하겠습니다. 뭐랄까, 저는 이 사진은 되게 이해가 잘 됐어요. 그러니까,
네.
충분히 이제 2차원에서 3차원으로 옮긴 거 이해가 되는데,
그렇죠. 네.
3차원에 있는 벡터를
네.
그냥 어떻게 그걸 2차원으로 그 줄일 수가 있는지 그냥 행렬 곱을 보면 그게
네.
이해가 되는데 뭔가 기하학적으로 뭔가 와닿지 않는다고 해야 되나?
그게
어떤 성분을 버리는 건지 어떤 건지.
버린다기보다는 이게 약간 이런 식으로 되는 거거든요. 이게 3차 이 그림이 조금 뭐 그렇긴 한데 이게
예.
지금 요 놈 있잖아요.
그렇죠.
요 놈이 우리의 그냥 2차원 평면이라고 해보세요.
네네.
그러니까 이게 3차원이에요. 예를 들면 3차원에서 3에서 2로 가는 거예요.
그렇죠.
이게 이제 2차원이고 여기 3차원이 점이 훨씬 더 많잖아요.
그렇죠.
그러니까 여기에 있는 어떤 한 점을 골라요.
네.
그러면 그 한 점은 여기 3차원에 많은 점들이 이 한 점으로 매핑이 되는 거예요.
그죠.
같은 점으로.
예.
그러니까 뭔가 버려진다라는 개념보다는 동일한 점으로 매핑되는 무수히 많은 어떤 3차원상의 공간, 3차원상의 벡터가 존재한다는 거죠.
그래서 그게
네.
그러니까 계산을 해보고
네.
뭐 그렇겠구나라는 건 이해가 되는데 뭐랄까 세밀한 과정이 이해가 안 될까 그 해야 되나?
그러니까 이게 거의 그 지난번에 배웠던 그 리니얼리 디펜던트라는 개념 있잖아요.
네네.
리니얼리 디펜던트에서 내가 이게 어디 설명했더라. 내가 이제 그런 얘기를 좀 했었던 적이 있어요. 그러니까 이게 네. 요 그림에서 그러니까 어디선가 그러니까 원점에서 출발해서
예.
일단 집을 떠나서
네네.
갔다가 다시 돌아와서 또 원점이 된다.
네네.
이런 얘기 했었던 적이
그죠.
있잖아요. 이게 그러니까 해가 이제 같은 어떤 b라는 값을 만들어내는데
예.
이제 갔다 올 수가 있으니까 뭐 이렇게 크게 갔다 오든 작게 갔다 오든 이게 여러 개가 다 가능해지는 거예요. 그렇죠.
그죠.
네, 이거 갔다 온다라는 것 자체가 이 우리의 정의역에 해당하는 이 3차원 공간에서 여러 개의 서로 다른 벡터들이 해당이 되는 거예요.
그러니까 어차피 돌아오는 점은 이제 같아지는데
네.
좀 더 멀리 돌아갈 수도 있고.
네, 그 여러 가지 초이스들이 있고. 근데 결국은 어떤 도달하는 점은 똑같으니까.
그럼 이거 뭐 이렇게만 올 수도 있고 이렇게 올 수도 있고 아니면 이렇게 올 수도 있고 이렇게 올 수도 있고 이런 걸 말씀하시는 건가요?
그러니까 여기서 중요한 건 이 어떤 돌아온다라는 거에서 요 각각의 초록색에서 쓰이는 어떤 그 벡터의 길이를 우리가 자유롭게 그 길이에 해당하는 게 우리의 솔루션 혹은 정의역에 해당하는 벡터가 되는 거죠. 인풋 벡터가.
그러니까 이 길이
그 길이가 그 길이 배수 그러니까 요 벡터 길이를 몇 배로 늘렸다가 돌아오느냐 그 몇 배에 해당하는 게 우리의 정의역에 있는 각각의 엘리먼트들이 되는 거예요. 왜냐하면 우리의 벡터와 매트릭스와 벡터의 곱은 요놈과 이제 요 놈들의 이제 선형결합이잖아요.
그렇죠.
결국 우리의 정의역에서 쓰이는 정의역에서 이렇게 뽑혀진 인풋 벡터가 과연 무슨 역할을 하느냐? 요 컬럼 벡터들의 리니어 컨비네이션 코에피션트로서 역할을 하는 거예요. 그러니까 결국은 요 코에피션트가 뭐냐? 결국 주어진 벡터들의 어떤 배율이라는 거죠. 그러니까 그 배율이 굉장히 다양하게 존재할 수 있다는 거죠. 같은 점에 도달하는 게.
알겠습니다. 이게 좀 이해가 되네요 이제. 그리고 나머지 하나의 질문은 그냥 이거 제가 잘 이해를 했는지에 대해서 여쭤보는 건데 예를 들어서 이제 4차원에서 3차원으로 이거 옮긴다고 했었을 때 피벗이 2개밖에 없다라고 하면은 이제 뭔가 쓸 수 있는 벡터가 2개밖에 없는 거고 그 2개의 벡터로는 2차원밖에 표현이 안 되는 거잖아요.
그렇죠.
그러면 그 도메인이 4차원이고 4차원이 어떤 그래서 무수한 점들이 있는데 그 점들을 이제 3차원으로 옮기려고 했는데 그 코 도메인이 3차원인데 어쩌다 보니까 이 2개인 것 때문에 레인지는 또 이제 2차원이 돼버리는 약간 이런 형태가 되는 건가요?
맞아요.
네,
알겠습니다.
맞아요. 제가 잘 이해하고 있는 건가요?
지금 일단 말한 건 다 맞아요.
감사합니다.
그러면 열심히 해서 보기 좋네요.
감사합니다.
네.